Hello, welcome to Quantitative Neuroscience and Mathematical Method in Neuroscience. My name is Ji-hwan Myung at Taipei Medical University. This is week 5. This week is about a simple T-cell model. We are continuing our discussion from last week. Last week we talked about the receptor binding, kinetics. And this week we're going to talk about the intracellular signaling that comes after the receptor binding. But before that, let's recap. In this week's lecture, I created these bubbles, cartoon bubbles, so you can just read these and understand the material without having to listen to what I'm just saying. So you can just rely on the lecture note, but just in case, because this lecture note is a bit different, we have a lot of information. I wanted to give you a short, brief note on how to understand. So what's important from the previous lecture was that there was an in rate and out rate. Now we have to think about the change of terms because although when you say in rate and out rate, we're actually thinking about the leaky water tank. Water comes in, water goes out. But now we're talking about the ligand binding on the receptor. So we have different names for it. First thing is the dissociation constant, which is a very, very important concept. As you have just noticed last week, dissociation constant tells you just how little ligand is enough to bind to the receptor and activate it. This basically tells you the affinity, binding affinity. And in fact, if you try to find the literature about dissociation constant, you would have to use the search word affinity because the binding affinity is actually more common usage of the word. And instead of the in rate and out rate, because the ligand binds on the receptor, it's instead called on rate. And after a while, the ligand will be torn off. It will lift off the receptor. So it's called the off rate instead. So these terminologies tell you about the same concept, but it will be important to know those words because you might be using the same context with different biological context. Now, to be practical, it's very important to have a sense of the quantity. The concept that we have developed without a context doesn't really mean anything. And what gives the context to our concept are these numbers, the ballpark range of the concentrations of molecules that we're considering, the so-called the physiologically relevant quantities. But what determines these quantities is actually the KD, the dissociation constant, or the binding affinities. So let's look at the approximate receptor binding affinities for some known receptor types. I'm giving you some numbers from very brief survey. So this might be incorrect, but they are certainly within a ballpark range. And also notice that I'm giving you the orders of magnitude. That means that if actual binding affinity is 5 nanomolar, I'm only saying 1 nanomolar, because it's within the nanomolar range. It's 5 times 1 nanomolar. That's why we call it 1 nanomolar. This is called the order of magnitude. And also, important thing to notice is that this is a chemical reaction. So the binding affinity should depend on temperature because we're talking about a chemical reaction. But then we notice that the binding affinity, which is the dissociation constant, is the reverse rate versus the forward rate. And what changes the rate is temperature, of course. If the temperature increases, the rate will increase. But in as much as forward rate increases, the reverse rate will also increase. And they are in ratio, so they will probably cancel out. So basically, the approximate value for KD doesn't really change, but it does change slightly, and its kinetics also changes. It's important to know. And also, we are we need to realize that all those ligand binding is based on ionic interactions. So its strength of binding will depend on the ionic environment where this ligand is in. So depending on the electrolyte concentrations, your binding affinity might change. And most of the time, we are deriving the KD values from some experimental setup, and that experimental setup may not be completely physiological. So your KD value can vary a lot, but nonetheless, there's a ballpark range. And here's a ballpark range. And as I said, LPS to TLR binding, the ballpark range is about 1 nanomolar. But this is slightly different when you're comparing with the classic neurotransmitter glutamate. When it binds to NMDA receptor, which is also the most representative glutamate receptor, the ionotropic glutamate receptor, NMDA, its binding affinity is actually about between 100 to nanomolar. So I'd say in between, it's about 10 nanomolar. And GABA to GABA A, which is also ionotropic GABA receptor, this is actually a chloride channel. Binding affinity of the GABA A receptor to GABA is just about 1 nanomolar. In comparison, the metabotropic melatonin receptor, MT1, its binding affinity is about 0.1 nanomolar, which is 100 picomolar. And arginine vasopressin, which is an important neurotransmitter in the brain, particularly in the circadian biology, its binding affinity to the V1A receptor, one of the receptor subtype for the vasopressin, is about 0.1 nanomolar as well. But it can be up to like 1 nanomolar. The values vary a lot, but once again, we need to have some ballpark range. One thing that you have to have in mind is that these numbers, the KD numbers, actually matters a lot. These KD values, these binding affinities, can be an approximate indicator of the range of ligand concentration. So in the case of LPS, which is a harmful molecule, it comes in a large quantity. It can be like 1 micromolar or even higher. So TLR receptors binding affinity of 1 nanomolar is totally enough. This is one of the main points that I stressed in the previous lecture. So its binding affinity of 1 nanomolar is incredibly sensitive if you compare with the actual concentration of LPS. And now you're surprised that glutamate receptor doesn't seem to be that much sensitive. Well, that's really because in the synapse, the glutamate concentration can be like, 1 to 10 millimolar, which is much higher. Nonetheless, the glutamate doesn't exist for a long time in synapse. But the glutamate concentration is so high that 10 nanomolar of binding affinity is totally enough to activate NMDA. You can say the same thing about the GABA. GABA in the synapse will also exist in the range of millimolar. But these neurotransmitters exist in high concentrations in the highly crowded area called the synapse. But hormones and neuropeptides are a bit different because they exist in a large space, such as the plasma or the CSF. Its values in physiological range is low. I think the melatonin, in the case of melatonin, it exists in the range of micromolar. So because melatonin doesn't exist in high concentration in plasma, the melatonin receptor's binding affinity is also high. So the KD is low, about 0.1 nanomolar. In the case of ABP, also the binding affinity is high, between 0.1 to 1 nanomolar. So we have those ideas. The question is, what would be the ballpark range of KD of inhibitors of these receptors? You can go ahead and find out about it, but quite naturally you can say that if the inhibitor is competing against the actual ligand, and it must have a larger quantity to completely inhibit. Well, what happens is if you have a higher binding affinity to the receptor, what's going to happen is the inhibitor will bind to the receptor, and thus it will prevent binding of the actual original ligand. So a good inhibitor will have a higher binding affinity, even compared to the binding affinity to the original ligand. But in the ballpark range, they have approximately the same binding affinity to the original ligand. That will be the answer.